Welcome back to The Explainer, Focused Learners. Today, we're injecting some serious data-backed reality into the AI engineering space. If you're building RAG systems, Retrieval-Augmented Generation, you've definitely had the chunking conversation. You know the one. Someone on the team insists that the newest hyper-complex semantic chunking method is just strictly better than everything else. Well, today, we're skipping the industry hype, and we're looking at the hard data to see what actually works in 2026. So I've got to ask right out of the gate, are you sabotaging your RAG system? Seriously, are you blindly following expensive best practices that are actually degrading your system's performance? We see developers doing this all the time, implementing overly complex pipelines just because of shiny object syndrome, completely unaware that these fancy methods might actually be tanking their retrieval accuracy. And getting this right, the stakes are absolutely massive right now. Recent data from Menlo Ventures shows that enterprise adoption of RAG just hit 51%. That's up from only 31% the year before. RAG isn't an experimental toy anymore. It's actively powering daily workflows all over the world. When more than half of all enterprises are using this tech, optimal performance isn't just a nice-to-have. It is mission-critical for your business operations. Section 1, the hidden RAG bottleneck. Okay, let's dive right into the first major hurdle developers face when building these systems. It's a step that often gets treated as a total afterthought, but it acts as a massive hidden bottleneck: text chunking. Before an AI can read your documents, those documents have to be sliced up. That's text chunking, the crucial pre-processing step of breaking a continuous document into smaller, discrete segments before embedding them for large language models. You literally can't just feed a 100-page manual into an embedding model all at once. You have to chunk it. But how you choose to cut that text changes absolutely everything. Why does this matter so much? Because the wrong chunking strategy creates up to a 9% gap in recall performance. That is the fundamental difference between an AI that instantly grabs the exact right answer for a user and one that hallucinates or just frustrates them until they abandon the tool entirely. And with the RAG market projected to hit $9.86 billion, a 9% performance gap isn't a rounding error. It is a multi-billion-dollar problem. Section 2. Meet the chunking contenders. Let's look at the playing field and see what our options actually are when slicing up all this data. A really comprehensive benchmark by the Vecta R&D team, which was detailed alongside an extensive 2026 analysis by Firecrawl, put 7 main chunking strategies to the test. They looked at basic fixed-size chunking at 512 and 1024 tokens. They tested LangChain-style recursive character splitting. They analyzed the highly hyped semantic chunking. Then they looked at structural methods, like document structure-aware splitting and page-per-chunk boundaries, alongside super complex LLM decomposed proposition chunking. And finally, a newer hybrid method called late chunking. If we categorize these, we're essentially looking at a battle of simple versus fancy methods. The simple methods? They're fast, cheap, and rely on standard rule-based splits, like hitting a specific character or token count. The fancy methods are highly complex. They rely on large language models or embedding-based similarity calculations to analyze the actual semantic meaning of sentences, dynamically slicing the text right where the topic shifts. Naturally, everyone just assumes the expensive, fancy semantic methods must be strictly better, right? Well, let's look at the data. Section 3, the benchmark showdown. The Vecta team tested these contenders on a dense corpus of 50 academic papers, pretty much the absolute hardest case for an AI to parse properly. But what makes this specific benchmark so interesting is how it was designed. You see, most chunking tests are fundamentally flawed because they use a fixed top K retrieval. Basically, if you always pull the top 10 chunks, a strategy making 1,000 token chunks gets 10,000 total tokens of context, while a strategy making 50 token chunks only gets 500. The large chunk strategy wins by default just because it grabbed way more text. So to make this a perfectly fair fight, the researchers used an adaptive K method. Every single strategy was given an exact context budget of roughly 2,000 tokens. Nobody could cheat by just hogging the context window. With the playing field leveled, the results of this showdown were honestly mind-blowing. The standard, totally boring recursive character splitting at 512 tokens absolutely crushed the competition. It hit 69% accuracy. Basic fixed-size 512 was right on its heels at 67%, and that highly hyped semantic chunking, it completely collapsed, coming in at a dismal 54% accuracy. As the Vector R&D team so bluntly put it in their report, the boring strategies won, the hyped strategies failed. It turns out that the relationship between chunk granularity and answer quality is vastly more nuanced than the industry hype wants you to believe. Newer and more expensive absolutely does not mean better. Section 4. Why fancy strategies fail. So, we have to ask the obvious question. Why did the fancy, expensive strategies fail so miserably in a controlled environment? Well, the answer lies in a rather shocking number. 43 tokens. Out of those 50 dense academic papers, semantic chunking produced over 17,000 separate chunks, and the average size of those fragments, a microscopic 43 tokens. Here is the crucial issue. Semantic chunking optimizes for what we call boundary purity, but it totally destroys context coherence. Because it works so incredibly hard to separate different ideas, it creates these tiny, isolated fragments. Now, think back to our fair fight budget of 2,000 tokens. A retriever trying to fill that budget has to grab roughly 46 of these tiny, disconnected chunks. Sure, it might successfully pull from the correct page, but 46 disconnected sentences, stripped of their surrounding paragraphs, do not form a coherent narrative. It's like grabbing 46 random pieces from a jigsaw puzzle and expecting the AI to somehow see the whole picture. The LLM gets this fractured, chaotic input, and it simply can't generate a grounded, correct answer from it. And this isn't just one isolated study either. A recent systematic analysis published on Archive independently confirmed this exact same thing. They stated, computational costs are not justified by consistent performance gains. Forcing an LLM or an embedding model to analyze every single semantic boundary in your document isn't just slightly worse. It is a massive waste of your budget and your compute power. This brilliantly illustrates the fundamental trade-off in all RAG systems, the granularity trade-off. Smaller chunks, like our 512 token recursive winners, let you pull 5 precise, highly targeted locations into your prompt. It's like throwing 5 highly accurate darts at the text. That gives you the highest answer accuracy. Larger chunks, like a 1024 token split, only let you pull 2 chunks. Yeah, you get higher document level coverage, but if even one of those large chunks is off target, you've instantly wasted half your context budget, and your overall accuracy drops down into the high 50s. Recursive 512 hits the absolute perfect sweet spot between targeted precision and giving the LLM enough surrounding context to actually understand what it's reading. Section 5. The Ultimate Decision Framework. Let's turn this into some practical, everyday application. I want to give you a data-backed decision framework that you can literally take to your engineering team today. Based on all the research across Chroma, NVIDIA, and Vecta, here is your 3-step playbook to optimize your baseline use cases. Step 1. Default to recursive character splitting at 400 to 512 tokens. This should be your starting point 80% of the time. Step 2. Apply a 10 to 20% overlap, so roughly 50 to 100 tokens, just to ensure a thought doesn't get abruptly cut in half at a hard boundary. And step 3, always test 2 to 3 simple strategies on a small sample of your own data before you ever start paying for expensive semantic API calls. To make it even easier, here's a quick chunking matrix for you. If you're processing general academic papers, web articles, or just plain text, rely on recursive character splitting. If you're dealing with heavily formatted PDFs, financial reports, or complex visual layouts, use page-level chunking. Fun fact, page-level actually dominated NVIDIA's 2024 benchmarks specifically for paginated PDF documents because it naturally keeps tables and figures perfectly intact on a single page. Finally, if you're on a tight budget and just need maximum speed, fall back to simple size-based chunking. Now, before we wrap, I do want to briefly mention one really fascinating new development called late chunking. Instead of splitting the text before embedding, late chunking runs the entire document through the transformer first, so the model understands the full context, and then it applies your standard boundaries on top of that. It preserves cross-references beautifully, so if a pronoun in chunk 3 refers back to a name in chunk 1, the system still gets it. It's a brilliant structural layer you can place right on top of your boring-leaning recursive strategy for even better context retention. So, as we wrap up this explainer, I want to leave you with a provocative thought to challenge your current setup. Take a hard look at your architecture today. Look at those API bills and ask yourself, how much is your overly complex RAG pipeline needlessly costing you right now? The data is crystal clear. Sometimes the most boring standard methods aren't just vastly cheaper, they are objectively better for your AI. Thanks for joining me, Focused Learners, and I'll catch you in the next explainer.